Okay, so there are some rules that we need to remember from algebra that they're also going to help our life simpler when we're going through to take the derivative. And so a couple of things that are helpful. If you have a variable in the denominator in just one term, so let's say you have 1 over or some number, b raised to the nth power. We can rewrite this by moving this b to the n into the numerator. So this would be b to the negative n power. So where that could be helpful when we're taking the derivative, for instance, let's say we had the example of f of x is equal to 1 over x cubed, and they want us to find the derivative. Well, right now we don't have the tools to do that. We'll learn hopefully at the end of class or near the end of class that quotient rule. So, but right now we can manipulate this function so that we can use the rules that we know. And so I'm going to use this rule of exponents, and I'm going to bring this x cubed that's in the denominator and rewrite it in the equivalent form, which is the same thing as x to the negative 3 power. And so now this is in the form that I can go ahead and use that general power rule. So taking the derivative of f of x, we bring our power down front, which is negative 3x, and we subtract 1 from the power. So negative 3 minus 1. So this is going to be equal to negative 3 x to the negative 4 power. Because I started this example and the x was in the denominator, I would probably rewrite this so I didn't have any negative exponents. And so you're only bringing down that piece, x to the negative 4, down to the denominator to make that exponent positive. And so this is equal to negative 3 all over x to the 4th power. Okay, so there was one rule. The other rule here was if they had a negative exponent and it was in the numerator, so b to the negative m, we can bring it down to make the b to the m down, make that exponent positive. Other rules that are helpful are if you have division. So let's say, for example, we have b to the m divided by b to the n. So if we have a case where we have the same base division, then we could take the exponent on top, subtract off the exponent on the bottom. This is actually equivalent to also, we could say, and sometimes this will be helpful when we're rewriting it, 1 over b, the exponent on the bottom, minus the top. So these are equivalent. It just depends on it. Are we trying to keep the base in the numerator or denominator there? And so here's an example where that could be helpful. So let's say we have our function, let's call it g of x this time. And let's say we have it as x squared minus 6x minus 10 all over x cubed. And we want to take the derivative of this. So right now, again, I don't have the rules of using the quotient rule, where we have some function on top divided by some function on the bottom, but I can manipulate this because this is a single term down here. We can rewrite this as 3 separate fractions. So let's just manipulate g of x to get into the form that we know how to take the derivative. And so this is the same thing as x squared all over x cubed minus 6x all over x cubed minus 10 all over x cubed. So to use that general power rule, we just need the variable in the numerator. And so let's rewrite this. We didn't want the derivative yet. So g of x is equal to, well, x squared over x cubed. I want that in the numerator, so let's use this rule. So I'm going to take the exponent on top, 2, minus the exponent on the bottom, 3. So that's going to give me x to the negative 1 power minus 6 Using this rule again, I'm going to take the exponent on top, which is not shown as 1, minus the exponent on the bottom, 3. So 1 minus 3 is x to the negative 2. Minus 10, and let's bring that x cubed up into the numerator. And we can rewrite it that way. It would be x to the negative 3 power. So now we've manipulated this function into the form that we can use our rules of derivatives that we know. So we have derivative of g of x, bring our power down front for our first term, which is negative 1, x, subtract 1 from our power. So negative 1 minus 1 is negative 2. Minus 6 times, bring our power down front, negative 2, x, subtract 1 from our power. So negative 2 minus 1 gives us a negative 3. Minus 10 times our exponent, which is negative 3, x, and now subtract 1 from that exponent. Negative 3 minus 1 is negative 4. So we get negative 1. But now we're going to use that rule. If you have a negative exponent in our numerator, we can bring that down to make that exponent positive. So this will be negative 1 all over x squared. Negative 6 times negative 2, so this is a plus 12. Bringing down that x to the negative 3 to make that exponent positive would be x 12 over x cubed. Minus 10 times 3, so minus 30, all over x to the negative, all over x to the 4th. So we could manipulate this a little more. So maybe because this was a single fraction here when we started, maybe we should rewrite this as a single fraction. And to do so, we would need a common denominator. So looking at x squared, x cubed, and x to the 4th, if I wanted to combine this as one fraction, my LCD is x to the 4th. And so multiplying each fraction by a fancy 1 to get that common denominator if we don't already have it. So this is where it would be helpful to know the rules of exponents if you're multiplying with the same base. And so if you have b raised to the m power times b raised to the nth power, remember you add your exponents. So this is b raised to the m plus n power. And so I need to get this in x to the 4th. I think to myself, what do I add to 2 to get 4, which is 2. So I need to multiply this by x squared over x squared. What do I add to 3 to get 4? Well, that's 1. So I have to multiply this 12 over x cubed by x over x to get the LCD of x to the 4th. And so doing that, we get g prime of x is equal to negative x squared plus 12x minus 30 all over our LCD. Now we can put it all over our common denominator, x to the 4th.
Can I ask a question real quick about it's like the third step down? We put the negative 1 out in front of the x.
Mm-hmm.
Yeah. And where did you get that negative 2 from? The exponent.
Because so from this point, I was taking the derivative, and so I was bringing down the negative exponent, my negative 1 exponent, which is here, and then I have to subtract 1 from my exponent. So negative 1, which was my original exponent, minus 1.
Oh, gotcha.
Negative 2.
Okay.
Yep.
Got it. Thank you.
You're welcome. Any other questions on that?
Yeah, I have a question on the same step. How come the 3 was not negative, but the negative 1 and negative 2 that you put in was negative?
Like here, right? Negative 3 here.
What we're at?
I'm right. Hold on. Let's see. Right here. So same, right? This point right here.
The where it says negative 10 times 3. How come that's not a negative 3?
This is a negative 3. Is it not showing up negative right here?
No, one below it.
Oh,
Sorry.
okay, sorry. It should be negative. Thank you.
Okay.
So this should have been a negative 3. So it's just going to change things a little bit. I should have brought down that whole exponent. And I forgot that negative sign. Good catch, -3. And so the only thing that's going to change in our problem is this -3 times -10. This is now going to make this a positive. Let's make it a positive. Good job. Thank you for catching that before I stop that video.
Thank you.
Sometimes I do that on purpose, not subconsciously. So I'm just checking to see that you guys are awake, and you are. You passed the test.
So then, Professor, so then you just kind of like manipulate it to get the same denominator. You can just like in other problems just to get the same denominator.
Yeah, so because at this endpoint right here on this part, I just had fractions, right? And so in order to add fractions, we have to get a common denominator. So that's where you would just look at the denominator and see what's the least common denominator that they would share in common if we wanted to add those fractions together. Any other questions?
Yeah, on the two rules on the left side,
Mhm.
are those both like actual rules, or one has a star on it? Is that the one we're using right now?
I was using both of them. So the first time I was using the one with a star to rewrite g of x as multiple fractions. So from this, actually, that's really from this step here. So once I rewrote it as multiple fractions, my g of x, then I was using this rule so that I can bring my variable x up into the numerator. So subtracting the exponents there. But actually, and let's see, actually the other one I did not use this one in this problem.
Okay.
If I wanted to, let's say, rewrite it, actually it doesn't matter. It doesn't matter. I did use that rule back up here in this example, I think, where we brought it down to the denominator. It's more of this one. But they're just rules of exponents that we're using to rewrite our function to help us take the derivative, to be able to use those rules that we know right now.
All right.
Okay, so another rule that's going to be helpful for us is to be able to rewrite a term with a radical without that radical. And so recall that we could rewrite terms with radicals. So for instance, square root of x, we would say this is the same thing as x raised to the 1/2 power. There's a general rule that says, okay, if you have some index, it doesn't have to be a square root. So maybe we're taking the cube root or the 4th root or the 5th root. So we're going to write it as n. So if we have the nth root of x and x is raised to some power m, there's a couple ways that we can rewrite this. This is the same thing as the nth root of x and then raise it to the m. But this nth root, whatever index you have, this is not shown, it's a 2, goes in the denominator when we rewrite it with a rational exponent. So this would be x raised to the m divided by whatever root we're taking. And so in this case, n. So the nth root of x to the m is equivalent form without the radical is x raised to the m divided by n power. And so now when we have a term that has a radical in there, we can rewrite it with a rational exponent, and then we can use that general power rule. So for instance, let's say we had f of x is equal to x minus 2 all over the cubed root of x. And again, we want to take the derivative of this. So right now, again, this is in the form where I could use the quotient rule if I knew that rule, or I've given it to you, but I haven't. So we got to manipulate this in order to be able to do this. And so because there's only one single term down here in the denominator, I can break this up as multiple fractions. So this is the same thing as f of x is equal to x divided by this cubed root of x minus 2 divided by this cubed root of x. We can rewrite it so that this no longer has radicals. So x over the cubed root of x is the same thing as x to the 1/3 power. So x over x to the 1/3 power minus 2 over x to the 1/3 power. So let's use rules of exponents so that we can simplify this. Same base x and its division. So let's take the base at top, x, take that exponent 1 and subtract off the exponent on the bottom 1/3. So minus 1/3. Minus, let's bring the x to the 1/3 in the second fraction up into the numerator, and let's make that would make that a negative exponent, negative 1/3. So in order to take 1 minus 1/3, we need a common denominator. So think of that 1 as 3/3. So 3/3 minus 1/3, this would give us x to the 2/3 power minus 2x to the negative 1/3. So now it's finally in that form where we can use that general power rule. So now we can take the derivative of this function. And so using the general power rule, bring our power down front. So 2/3 is our power, x, and then we're going to subtract 1 from this exponent. So 2/3 minus 1. If this is ever a fraction in here, when I'm subtracting my 1, I rewrite it in terms so it has the LCD. So I'm going to write my 1 as minus 3/3. Minus my coefficient in front of the second term, which is 2, times my exponent, which is negative 1/3, x. And now I'm going to take my exponent negative 1/3 and I'm going to subtract 1. So in this case, again, I'm going to rewrite my 1 as 3/3. So this is equal to 2/3 x. Well, 2/3 minus 3/3. So 2 minus 3 is negative 1 all over 3. And then negative 2 times negative 1/3, so that's plus 2/3 x. So negative 1/3 minus 3/3 is negative 4/3. We can now use rules of exponents. We have a negative exponent. We can bring it down into the denominator to make that exponent positive. So this is equal to 2 all over 3x to the 1/3 power plus 2 all over 3 raised to the x time 3 times x raised to the 4/3 power. If I wanted to combine this, this is our derivative as a single fraction, which is going to be helpful for us when we're trying to find out when this is equal to 0 or where it's undefined, is to rewrite this as a single fraction. So let's just do that. And so our least common denominator, if I have a 3x to the 1/3 and a 3x to the 4/3, well, we know 3 has to be in there for our least common denominator. So our LCD is 3. And we need the highest variable, so x to the 4/3. The variable raised to the highest exponent, so 4/3. So I'm kind of thinking to myself, what do I have to, remembering base rules of exponents, same base, I'm going to be multiplied by this fancy 1, but what do I have to add to 1/3 to get 4/3? Well, I need to add a 1. 3/3 plus 1/3 is 4/3. So I need to multiply both the top and the bottom, my fancy 1, of the first fraction by x over x to get that LCD. So this would give me 2x all over 3x to the 4/3. And then plus, so I have my LCD now, 2. And just because I started with radicals in my original problem, I would probably go back and I would rewrite this x to the 4/3 as a radical. So this is equal to 2x plus 2 all over 3. So the exponent, the denominator of the exponent is the radical, what root you're taking. So we're taking the cubed root of x, and the numerator is 4. So the cubed root of x to the 4th. So I would probably leave it like that. I notice I could technically pull an x, that's x to the 4th, same thing as x times x cubed. So I could technically take the cubed root of x cubed and pull out an x out front. Okay, so our next example, we have a function f of x equals the quantity 3x minus 4, and that quantity is squared. And again, we want to find the derivative. Of f of x, so f prime of x we want to find. So again, we don't have the tools right now. A little bit later, hopefully this week, that we'll learn this, what it's called the chain rule. We could use the chain rule to differentiate this, but right now we don't know that chain rule. And so let's manipulate it so we can take the derivative with the rules we do know. And so all I'm going to do is first I'm going to rewrite this. So the square out here is just telling me I'm taking my f of x, I'm taking what's inside the parentheses and multiplying it by itself twice. So this 3x minus 4, that quantity squared, is the same thing as 3x minus 4 times 3x minus 4. I'm going to show you the product rule in a minute, but right now we don't know that product rule. And so I still can manipulate this a little more by distributing and adding like terms. So 3x, let's distribute the 3x to each term in here. And so 3x times 3x, that gives us a 9x squared. 3x times negative 4, so that gives me minus 12x. And now let's distribute the negative 4 to each term. So negative 4 times 3x, again, that's minus 12x. And negative 4 times negative 4 is plus 16. So f of x is equal to, combining like terms, only like terms I have are negative 12x minus 12x. Same sign, so add, keep the sign the same. So 12 plus 12 is 24, so minus 24x plus 16. So now we've manipulated this function in terms of the way that we can use this general power rule. And so now we can take this derivative of f of x. We have 9 times, so bring our exponent down front, 2, x, and subtract 1 from our exponent. So 2 minus 1. Then our coefficient in front of the next variable, negative 24. So bring our exponent down. If there's no exponent here, it's 1. So bring our 1 down, x, and then raise that to the 1 minus 1 power. Plus the derivative of a constant. So the derivative of 16 is 0. So we get our derivative of f of x is 18x minus 24. So let's just try it. Let's say we didn't know that. We didn't know to do that. Is the derivative is f of x equal to, how about in this form, 3x plus 4 times 3x plus 4. Is this the same as looking at the derivative of the first? So I can write that as d times dx of the first 3x plus 4 times the derivative of the second function. So if this was limits, we could break it down like this. And we had multiplication of two functions. But I want to know, can I do this with derivatives? Can I just take the derivative of the first times the derivative of the second? So let's try it. We know what the derivative is. We found it over here. And so if I take the derivative of the first piece, well, the derivative of 3x, that's just 3. The derivative of 4, or derivative of a constant, that's a 0. So it's 3 plus 0 times the derivative of the second piece. Well, the derivative of 3x is 3, plus the derivative of a constant is 0. If we did this, this would be 3 times 3, which is equal to 9. Notice these are not the same thing. So we cannot take it, the derivative of the first times the derivative of the second when we're using the product rule. So let me give you what the product rule says. Okay, so it depends on what notation, but it means the same thing. Let's say that we have some function f of x, and it's equal to some function g of x times another function h of x, where g of x and h of x are both differentiable. Then the derivative of f prime of x, or the derivative of f of x, which is f prime of x, is equal to the derivative of our first, g prime of x, times the second function h of x, plus the first function g of x, all times the second function, derivative of the second function, h prime of x. Okay, so if that is the rule, and we wanted to go back and use that product rule in that last example. So that last example, we had what, 3x minus 4 quantity squared. Let's use the product rule. Derivatives to solve, to find f prime of x. Okay. So we first have to rewrite it as a product. So first one would be 3x minus 4. That's 1. And then the second one would be 3x minus 4. So taking the derivative of our product, we look at the derivative of the first function. So looking at the derivative of this first function. So derivative of 3x is 3. Derivative of our constant negative 4 is 0. So 3 times the second function, which our second function is 3x minus 4, plus the first function. Well, the first function in here was the 3x minus 4 times the derivative of the second. So the derivative of this 3x minus 4, well, derivative of 3x is 3. Derivative of the constant is 0. So let's just distribute and combine like terms. So the derivative is equal to, so distributing this 3 times 3x is 9x. 3 times negative 4 gives us minus 12. Now let's distribute our 3 here. So 3 times 3x, so that's plus 9x. And minus 4 times 3, so minus 12. So 9x plus 9x is 18x minus negative 12 minus 12 is minus 24. So notice this is the same exact thing that we got when we had taken it by first expanding it out right here. These are the same. So notice there were different ways that we could do to find the derivative of a function. And so sometimes it's just looking to see, can I manipulate this a little bit more so that maybe when I go and take that derivative, it's going to fall out nicer. So sometimes some ways are easier than other ways. And so it's just kind of recognizing and manipulating to make life as easy as possible. Okay, so the next example we have here says we want to, for each function, or this function f of x equals x cubed minus 5x squared plus 6x plus 3, we want to find all values of x where the tangent line is horizontal. And so we kind of have to decipher what is that actually asking. So tangent line is horizontal. What do I know about a tangent line being horizontal? And so we know that tangent lines are the slope at any particular value on some function. And so notice that on this function here, my tangent line is horizontal. Well, if my tangent line is horizontal, that tells me then that my slope has to equal 0. So then f prime of x of 0, whatever that number is equal to 0. So I need to figure out actually the derivative, and I need to figure out when is my derivative equal to 0. And so doing that, let's look at the derivative. The derivative of f of x, it's already in that form. We can just go straight ahead and take the derivative. So using the general power rule, the derivative of x cubed is 3x squared minus, so 5 times my exponent, 2, x, subtract 1 from my exponent, it's 1. Plus the derivative of 6x is 6, and the derivative of 3 is 0. So this gives me 3x squared minus 10x plus 6. So I would see if I could factor this. I would try the AC method. 3 times 6 is 18. Now there are two numbers that multiply to a positive 18, but add to a negative 10. 2 and 9 don't work. 3 and 6 don't work. 18 and 1 don't work. So I know that it's not factorable. I don't see it. So if it's not factorable, and I notice this is a quadratic, we can use that quadratic formula. So recall, if you had ax squared plus bx plus c, some quadratic formula is equal to 0, then we say that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so negative b, so negative of negative 10. So x is going to equal positive 10 plus or minus, so plus or minus the square root b squared, so negative 10 quantity squared minus 4 times a. Well, my a value is 3 times c, and my c value, my constant, is 6. All over 2 times a, and again, my a value for my quadratic is 3. So let's just go through and simplify. We have 10 plus or minus. Well, negative 10 times negative 10 is 100. So 100 minus 4 times 3 is 12. 12 times 6 is 72. So minus 72 all over 2 times 3, which is 6. And simplify. So 10 plus or minus, well, 100 minus 72. So that is 28 all over 28 all over 6. 4 times 7 is 28. So recall, if we have square root of 28, we can break this down as the square root of 4 times 7. Since it's strictly multiplication, this is the same thing as the square root of 4 times the square root of 7. And square root of 4 is 2. So this is 2 root 7. So this is equal to 10 plus or minus 2 root 7 all over 6. So notice the numerator. Notice we have a 10 plus or minus this 2 and then the radical. Well, 10 and 2 both have a 2 in common. So we can factor that out in the numerator. And that way we'll be able to cancel with a factor of 2 from the 6 in the denominator. So if I pull out a 2 in the numerator, I would be left with 5 plus or minus root 7 all over my 6. And now that we pulled that out and it's multiplication in between, we can cancel like factors. So 2 goes into 6 3 times. So we just found what values of x set that denominator equal, not denominator, that derivative equal to 0, which is x is 5 plus root 7 all over 3, and x equals 5 minus root 7 all over 3. So this is where the tangent lines, or tangent line of f of x are horizontal.